This video will cover how to write quadratic functions given 2 points. Now, traditionally, we need 3 points to write a quadratic function. However, if one of the points we have is the vertex, then we only need 1 additional point. So we've discussed that a parabola is the shape for our quadratic functions. And one of the key points of the parabola is that vertex, which is going to represent either our minimum or our maximum, depending on whether or not the quadratic opens up or it opens down. Now, if I know where the vertex is, so I'll just plot some point here on my screen, and I've identified just some other point that this quadratic is going to pass through, then I know for sure that there's only one quadratic that could possibly pass through 2 points due to the symmetry of the parabola. So if I'm going to draw 1/2, because I know of the parabola extending from this vertex to begin with that passes through this point, due to the symmetry of the parabola, again, then I know the other half should look like a mirror image about our axis of symmetry, which passes through that vertex. So I only need 2 points to find this quadratic function equation. Now, because one of the points we're given is the vertex, we're going to use vertex form to ultimately write the equation of these quadratics. And as a recap, vertex form is going to look something like this, where we have y equals some constant value a times x minus h squared plus k, where h and k are also constant values. And in this format, it's very easy to identify transformations that have happened to the quadratic equation from its parent function, y equals x squared. So this is our most basic quadratic with nothing that has occurred to it from a transformation perspective. So we're going to use that x squared as our starting point and ultimately apply the necessary transformations with the aid of our vertex point and additional point to find the final quadratic function that would pass through the 2 given points. So let's jump into a couple examples. The first one, we have a vertex at -1, 4 passing through the point -2, -1. So again, we're going to use our parent function to begin. So we have y equals x squared, and we know the vertex is at -1, 4. And also, I'm using the knowledge that for the parent function, we have a vertex at 0, 0. So I'm asking myself, if the vertex originates at 0, 0 with the parent function and is now at -1, 4 for this particular example, what transformations would need to be applied to go from 0, 0 to -1, 4? Well, if I'm looking at a coordinate plane, 0, 0 being our origin, and I move over to -1, 4, to slide from that 0, 0 to -1, 4, we can see that we need to go left 1, up 4. And now that we have a background in how to apply transformations to functions, we're going to show that those 2 movements have occurred on our parent function to reflect the given vertex. So to move left, we're going to add 1 to our input variable, and we're going to move up 4 by adding 4 to our entire parent function x squared. So that's the starting point. We're going to use our vertex to show some translations in the original parent function. So now we have this quadratic equation, but we're not quite done, because there's an infinite number of quadratics that could pass through that vertex, but we have to make sure that we whittle it down to the 1 quadratic that would pass through that given vertex and this additional point, -2, -1. So if I plot -2, -1, that point here, there's only, again, 1 quadratic that's going to pass through this, knowing we have an axis of symmetry that passes through our vertex point, and leveraging the symmetry of the parabola. Ignore my poor artistic talent here to get our final equation. So the only thing that's missing is we need to consider what sort of a value could possibly be here for our final answer, because we don't know, just based on a vertex alone in a given point, just from looking at that picture, we don't know, okay, was there a reflection? Was there some sort of a vertical dilation? And we need to consider that as a possibility. So to do that, to determine what that a value is going to be, let's insert that a variable in our equation now. And we're going to use that point it passes through to plug into the x and y variable and ultimately solve for a. So if I substitute -1 in for y, we're looking for this a value, and I'm going to plug in -2 for x, and now we're going to solve for a. So just make sure we follow the correct order of operations here. We're going to get -1 in our parentheses. -1 squared is +1. A times 1 is just a. So now I have a plus 4 is equal to -1, and subtracting 4 from both sides will reveal that a is -5. And you can see that we have a negative a value indicating a vertical reflection has occurred. And from that previously drawn image, we did see that the parabola opened down just from plotting the point of the vertex and the point it passes through. So we should have expected a negative a value. But just looking at a picture, it is difficult to determine whether or not we have some sort of dilation, or I should say, by what scale factor that has occurred. So to finalize this, we're going to plug in that a value. So we have -5, and we're still going to show our translations to get to the desired vertex, which in this case required a left 1 up 4. And now I have a quadratic function in vertex form that would pass through that point -2, -1 with a vertex at -1, 4. Let's do one additional example to wrap up this video. So we have a vertex at 3, 0. So again, what I'm going to do to start is consider my parent function x squared, and using the knowledge that our vertex of that parent function starts at 0, 0, I'm going to determine how do I get from 0, 0 to 3, 0 through translations. In this case, all that requires is a slide right 3. So I'm going to show that right 3 by applying that proper transformation to my parent function. So to move right 3, we must subtract 3 from our input variable. So there is no vertical translation, so I don't have that plus k value. So now that I have the translations demonstrated into the parent function, again, we also have to consider the possibility of a vertical reflection or some sort of dilation. So we're going to add in an a variable that we're ultimately going to need to solve for by using that point it passes through. So we know, again, coordinates are coming in the form x, y, so our y value is 7. We have an unknown a value, and we have an x value of 1. And now we're going to solve this equation. So we're going to get -2 squared, and then we know -2 squared is 4, so we have 4 times a, divide both sides by 4, and we're going to get a is equal to 7/4. A positive a value indicates that this parabola opens up, and you should feel good about that, because if I plot 3, 0 and 1, 7, knowing that, again, there's only one parabola that would pass through these 2 points. So if I draw my left half of the graph using the symmetry about that axis of symmetry that passes through that vertex, I can see this parabola would have to open up. So now we're just going to finalize this equation by substituting that a value back into our equation in this step. So we have 7/4, which would indicate we did have a vertical stretch by that scale factor of 7/4, and we're moving right 3 to get to the desired vertex of 3, 0. And here is the quadratic equation that passes through the point 1, 7 and 3, 0. And just to double check to make sure that this is like if you want to use a final bit of arithmetic to make sure your answers are correct, if we plug in these points, the equation should balance out as something that is true. So for instance, if I want to check, does 3, 0 fall on this quadratic? Does 1, 7 fall on this quadratic? I can plug in those points. So I can say 0 equals 7/4, 3 minus 3 squared, 0 equals 7/4 times 0 squared, which is 0. 0 times anything is 0. So because I got 0 equals 0, which is a true statement, that vertex is in fact on that quadratic equation that I have written. And then I can also check 1, 7 by just seeing it. Does the equation result in a true statement at the end? So 7/4, we're going to get -2 squared, which is +4, and 7/4 times 4 we know is 28/4, which does reduce to 7. So 7 does equal 7. So there's a way that you could check your final answer to make sure that it is the correct quadratic that passes through those 2 points. Because again, if it works through those 2 points, you definitely have the correct quadratic. There is no other quadratic that could possibly pass through those two, under the assumption that one of those points is a vertex. And that's how we will conclude this video.